Welcome to Aryabhat Center for Theoretical Physics. Today we will learn about the black body spectrum. We will derive black body radiation law. So to derive black body radiation law, first of all we have to find the number of photons in a box if in the box the radiation is in thermal equilibrium with some atoms in the box. So to find the black body radiation law, we have to find the number of photons in a box if the radiation or photon is in thermal equilibrium with some atoms in the box. This is the box, this is the radiation, and this is atom. So we have to find the number of photons. In the rectangular box. Suppose for each light frequency omega, frequency of the light omega, there are n number of atoms in this box, n number of atoms, and frequency of the light is omega. These atoms are separated by two energy states. Two energy states. This is ground state, this is excited state. So these atoms have two energy state in the box. And the energy separation between these two energy state is delta E is equal to h bar omega. This is ground state, this is excited state. Delta is equal to h bar omega. Let n g is the average number of atoms in the ground state. Ng, and Ne is the average number of atoms in the excited state. Excited state. And this box is at thermal equilibrium at temperature T, and in this box these atoms have two states, G ground state, excited state, number of atoms is Ng and Ne, and thermal equilibrium of this box has temperature T. Then according to statical mechanics, Ne divided by Ng is equal to E to the power minus delta E divided by kT, or E minus delta E is nothing but h bar omega divided by kT. So this is according to statical mechanics. Now we know that any atom in the ground state can absorb photon and go into the excited state. So this is ground state, this is excited state. Any atom can absorb photon and can go into the excited state, and at the same time excited atom can release photon and go into the ground state. In the equilibrium, absorption must be equal to emission. So at thermal equilibrium, a rate of absorption equal to rate of emission. And the rates are proportional to the probability of the event, and the rate is proportional to probability of the event. Probability of the event. So suppose n bar is the average number of photon in any given state with frequency omega, then the absorption rate will be n ground state number of atoms n bar a square. This is the probability of the event of the absorption. Same way, the emission rate will be n e n bar plus 1 a square. This is absorption, this is emission. Excited state, ground state, excited state, ground state. Absorption rate is n g n bar a square. N bar is the average number of photons present in any given state, and emission rate is n e n bar plus 1 a square. A square is nothing but a probability of the event, and at thermal equilibrium this must be equal. So n g n bar a square is equal to n e n bar plus 1 a square, or n bar divided by n bar plus 1 is equal to n e divided by n g, or this is again equal to e minus h omega divided by kt, or n bar equal to 1 divided by e minus h omega kt minus 1. This is the average number of photons. Average number of photons in any given state in the box which has certain amount of atoms as well gamma radiation. So we have derived the average number of photons. This n bar equal to EH omega by KT minus 1 is the mean number of photons. So this photon is at thermal equilibrium at temperature T in the box. Now each photon has energy h bar omega. So number of photons had energy n h bar omega. So the total energy is h bar omega divided by E h omega KT minus 1. This is the energy in the photons. H omega divided by h omega KT minus 1. This is also the mean energy of the photon, or in the box, mean energy in the box. Now we have to find the black body radiation law. So we need to know about the modes, number of modes at each energy. So again we take a small box. In this box the frequency of the radiation is delta omega, and suppose there is a string, one dimensional string like this. We can ask how many modes are there for this one dimensional string. So the wave number is k is equal to 2 pi by lambda 1D string, and after finding the modes of this string we can generalize to get the number of modes in this box for the radiation. So the number of modes, first of all we have to find the wave number. Wave number k is, we know that 2 pi by lambda. For the wave number for the jth mode will be kj j pi by lambda, and here this is one mode, this is 2, and this is for the multiple modes. For one mode 2 pi by lambda. So the separation delta k between two successive mode will be, the separation between two successive mode will be delta k is equal to kj plus 1 minus kj, or pi by lambda. Delta k is pi by lambda, the separation delta k between two modes. Or if we take delta n as the number of modes in the interval delta k, then delta n is equal to delta k divided by delta small k, or delta k divided by pi by L or L by pi delta k. Delta n number of modes in the interval delta k is equal to L by pi delta k. This is the number of modes for the interval delta k. Or we can write delta n is equal to L by 2 pi delta k. There are 1/2 as many as mode, so it is the 1/2 of this one. So delta n equal to L by 2 pi delta k. Or kx is equal to jx by pi divided by L, ky is equal to jy pi divided by L, and kz is equal to jz pi divided by L. Or we can write the number of modes. This is for the 3 dimension, x component, y component, z component. So number of modes delta n k is equal to Lx, Ly, Lz divided by 2 pi whole cube delta kx, delta ky, delta kz. Or we can write this one as V, and this one is dqk. This is the volume in k space, volume in k space, and this one is volume V. So V divided by dqk, 2 pi to the power q delta n k. So this is the number of modes for the wave number for the in the volume in k space, 2 pi to the power q v dqk, this one. Again we know that the wave number k is related to the frequency by omega by c, and for the spherical cell the volume is 4 pi kq delta k, or delta n, the number of modes for the frequency omega is v 4 pi k square delta k divided by 2 pi to the power whole cube. Or we can write delta n number of modes delta n is equal to v 4 pi k square delta k divided by 2 pi to the power whole cube. Or delta n omega is equal to v 4 pi k is equal to omega by c. So it will become omega square delta omega divided by 2 pi to the power whole cube, or delta n omega is equal to v omega square delta omega divided by pi square cq. This is the number of modes, and we know that the each mode has the energy n h omega, n bar h bar omega, or h omega e h omega by kt minus 1, or delta E is multiplied by this and this. So delta n omega h omega divided by E to the power h omega divided by kt minus 1, or the energy will be delta E will be h bar omega E h omega divided by kt minus 1 v omega square delta omega divided by pi square cq. This is the black body radiation law. Omega is the frequency, delta omega is pi cq. This is the black body radiation law. Now there is a little introduction of exclusion principle. We know that every particle has some spin, and Fermi particle follows Pauli's principle, and Pauli's principle says that no two particles have same quantum state. So if there are two particles which are entangled with each other, then both pair have opposite spin, either up or either down. So this is the Pauli's exclusion principle. So this is the nucleus. Nucleus has spin up, then the electron which is revolving around the nucleus must have a spin down. No two atoms or electrons can have same spin, either up or down, opposite spin.